All right, we've changed rooms, so hopefully we can get Cygwin to work, Eclipse to work, things like that. May as well give that a shot. The Cygwin terminal should be right on your desktop. So should Eclipse. If you double click on Cygwin, we are now in the Cygwin terminal. I'm going to change my options so that we can see our size. Crank that up. Alrighty. Hopefully green's legible enough. So if I do ls, I see a bunch of things. Let's see if we can create a document in this directory. Did that work for y'all? Everybody able to get into Cygwin? If you're on your own machine, you may not have any luck doing that. So what I'm going to do is I'm just going to type ls into t.txt or jeff.txt. ls is the Unix version of dir. All right. It created a file called jeff.txt. Now I'm going to print that file out. Cat space jeff.txt. All right, and it printed the directory out. If you want to get a nice looking directory with more information than just a list of file names, do ls minus a. Well, that didn't do it. ls minus caps. Okay, that didn't do it either. Is it ls minus l?
Yeah.
All right.
ls a is permissions, I think.
Okay, okay.
Or ls.
ls minus.
A shows all the hidden ones.
Okay, cool. That's what I was thinking. Or that's not what I was thinking, but that's what I wanted, is everything. Okay, so if you do ls minus la, now this format is kind of crowded because we have some really long file names and stuff like that. But where in the world has it put me? I don't seem to be in a home directory. pwd, sig drive c users jg Thompson.
You can go to home after that, I think. Do cap.
All right. Well, what I'm going to do is I'm going to come here and look for jeff.txt, find out where it's hiding. So I'm going to right click. What I did is I just went to my search box. I typed jeff.txt. And I'm going to do open file location. And is it right on my desktop? Is that what it has done? All right, it's right on the desktop. That's what it has done. So if I want to make a subdirectory called home or C programs or something like that, I could do that. And I'm going to do that just for funsies. It's okay if this doesn't all work right now. If you don't have Cygwin installed on your laptop, that's okay. I just want to test it, make sure that we've got it going. Okay, type ls, remove the space after the hyphen. ls space. Yeah. Okay, cool. Now yours is set up properly because you installed it yourself. Okay.
Yeah, when I set mine up, it doesn't. It has like its own little folder.
Neat. Right. Okay. So William, our IT guy, made it pretty awesome so that our home directory is actually our Windows home directory, but that's not what I was expecting. So I'm going to make a directory for me. md space home. You don't have to do that. Okay, excuse me. mkdir space home. And I'm going to cd into home. Now I want to create a file in that directory. And honestly, it's been a real long time since I've used a text-based editor. So I'm going to cheat. I'm going to open up TextPad. If you don't have TextPad, well, let's just use Notepad. All right, so I'm going to crank up Notepad. And I'm going to do a file save as and go save it into my home directory. Whatever directory you're currently in. If you weren't able to find out where you were, do that trick about doing what I just did. ls arrow, or excuse me, greater than, make a file, go to the search box, look for that file, do a right click, open file location, and you'll see where that directory is. So I'm going to use Notepad to create a file in that directory. So file, save as, I'm just going to call it hi.c. Put it in my home directory, hi.c. All right, it's going to be the typical hello world program. # include less than stdio.h, main parentheses in parentheses, open brace. Yeah, C is awfully forgiving of things like that. Int main, printf, hello, \n, end parentheses in. I'm not going to put that system pause in here because I'm doing this from the command prompt. When I run it from the terminal, you know, I don't need a system pause. I'm going to leave it. I could put it there.
Do a return 0 instead.
Yeah, I need to put a 0 there. Okay, so when I'm in Cygwin, I can still launch Windows applications, but the path has to be set appropriately, and it doesn't seem to be. So that pause command wouldn't have worked anyways. I'm going to throw it in there just so I get to see the error message that it runs. Okay, so system quote pause end quote semicolon, and I'm going to do a return 0. All right, if I go back out to Cygwin now, I should be able to do ls. Let me make this. Sorry, I forgot to crank up the size of the font. There we go. I'm going to do an ls hi.c. Make sure the file is there. Or ls minus al. Yeah, it's there. Hi.c. I want to compile it. I'm going to use the GCC compiler. GCC space -o so I can create the output file. Hello is going to be my output file, not hello.exe, although I wonder if I could get away with that. Space hello.c. So this is the file that we are compiling, and we are making the output of it -o. I believe we could rearrange the order of that if we wanted to, so we could say GCC hello.c and then -o hello. Hi.c. GCC hi.c -o, and if I called it hello, it would make an executable called hello. Hi. All right. Implicit declaration of function. It didn't really like our system at all. I'm going to run it anyway. It's just for grins. Now, when I run it, the search path in Unix, in Bash, does not automatically include the current directory, so I have to specify it with a dot. ./hi. And it runs, and then it warns me that the pause command is not found. And so, if we did all of our programming from GCC now instead of Visual Studio, then I would never use pause again. I'm going to do that again. GCC hi.c -o hi. And then I'm going to do //hi, and I can see my hello there. Now for grins and giggles, I'm going to make the file name called .exe. GCC hi.c -o hi.exe. And now I'm going to try to run it. Hi.exe. Whoops, wrong slash. /hi.exe. By the way, it's Windows that's the aberration in using / everywhere. All right, cool. I might go with the idea that I like seeing the .exe extension, but it's optional in Bash, in Linux, and everything. Alrighty then. I want to see if we have Eclipse configured correctly. And if you're installing it on your home machine, it may very well not be. And I need to upload the document that I did about configuring Eclipse, because I sent one to the system administrator so he could get Eclipse going. So if you don't have Eclipse yet, that's fine. If you do and it's not working, that's fine. I'm going to launch Eclipse. And I didn't wander around and make sure that everybody got it compiled. Did it compile that?
Yeah, it worked.
It's okay to say no. All right, I'll be right there. Okay, I'm going to do launch, and then I'm going to pause so I can go see what's going on. All right, if you've installed Cygwin, I'm going to go and just make a note of that right on the front page. No, I don't want Windows Media Player. I don't know where you came up with the idea that I did. So on the machines in room 202, our home directory is our Windows user directory. When you install Cygwin on your own computer, the home directory may be in C:\Cygwin64 / home / username, where username is your username. Right, okay. Yay. Alrighty. Were you able to compile it? Do you need those commands back up in front of you again? So gcc space hi.c -o hi.
Says GCC error. No input files, no set file. We're ready to do the
Input file. Well, do ls -la.
what's that first command? .\.
Well, our .txt file is gone. Where did our .txt file go? Oh, is this the command prompt out of the Cygwin?
It's Cygwin. Fabricated.
Yeah. Tell you what.
Before we went to home.
Close and launch Cygwin again. All right, now do an ls. Okay, now there's high CC, so do the gcc command again. Alrighty, it doesn't like that pause command, but we'll delete it. Now run it. ./hi. And that's fine. That it says no command. You can delete that line. Alright, so I'm pretty happy that we've gotten Cygwin to work. Now if you haven't installed Eclipse, that's okay, but we're going to take a shot at running it. Those of y'all who are using this machine or did install it, Eclipse may be already, whoops, I already had it running. Okay. So I'm going to do File, New, C project. Let me back out of this because I'd rather be doing this with my notes. But okay, C manage build. Now I'm going to choose a empty project. Now I'm going to choose a Hello World project. And where it says tool chain, I'm going to choose Cygwin. And I would be astonished if this worked for everybody who just installed it. So I'm going to call this one Hello. And I'm going to click Next. Me, see author. Alrighty. Alright, so hopefully I'm in my project now. I don't see my okay. Where I got to my project list was by clicking the icon on the side. There's my little program. I'm going to run it. Launch file failed, binary not found. That's not surprising. So project build all. It scrolled for a while. It says that I have a building target done. I'm going to run debug. Selection cannot be launched. Okay, fine. I'm wondering where it stored it. If we could go and run it by hand. Run. Selection cannot be launched. Run. Okay, I had to click in the window itself to get it to run. And it said hello world. Now, when I installed Cygwin on my machine downstairs, I could not choose the GCC toolchain in order to get it to work. Instead, I had to use, let me get the file name, which I don't even see listed here. So I think I'll ask our IT guy, William, what he did in order to let the GCC toolchain actually work. But barring that, let me see. Dab, did you install Eclipse?
No.
Okay, okay. I'd like for you to install Eclipse before the next time we come, and then I'll have more of my ducks in a row. And is everybody else using the computers in here, and so it's working for you? Okay, all right. So we will punt on this for a little while. I want to get all my ducks in a row before I go further on this. Okay, so either way, we could be editing our code inside Eclipse or just with a simple text editor, old school. Now there are better text editors than Notepad. On these computers there's one called TextPad, for example. There's also, isn't there one called Notepad 64 or something like that?
Notepad++.
Notepad++. I haven't used, yeah, where are you? Fine. How about TextPad? Yeah, TextPad 8. So I'll play with doing that. We kind of need to pick an editor and run with it. Hopefully we can just use Eclipse from this point on. But I wouldn't mind being able to do more stuff from the command prompt as well. Specifically, I want us to work with creating libraries and make files using the command prompt. But for now, I want to get back into our lectures. All right, this is a mixture of stuff from our textbook and stuff that I created and stuff that I got elsewhere. But a variable, what is it? It's a named place in memory that has a type, an address that it points to, a value, and of course it's got a name. So our variable name might be operand 1, it might be an integer, an int. It was defined with an int. When we created it, we assigned it the value 29, and we found a memory address for it. I'm going to go back to Notepad and see if I can print out the memory address for a variable. So go back to your Notepad. We could just pop open Visual Studio and do this stuff. Make a variable called x, and then do printf %x. X should be a hexadecimal version of what we want to print. \n, end quote, comma, and then use the ampersand x, like that. And now I'm going to go back to GCC and I'm going to compile it again. I'm just going to hit the up arrow until I find the compile command. And then I'm going to run it again. ./hi.exe, or if you didn't add .exe to your compilation command. Okay, check it out. There's our memory address right there for that variable. You can use that memory address to actually change the contents of that variable. I'm going to go ahead and throw this in just because pointers and memory addresses are such an important part of C that even though the textbook doesn't get to them for a while, we're going to go ahead and see what they look like. I should have added them to the PowerPoint. Okay, I want to create a pointer to a variable. So I'm going to do int star px semicolon. Let me make sure that compiles before I go any further. Yeah. All right. And now I'm going to store the address of the x variable in it. So px is equal to ampersand x. Ampersand you can think of as meaning address. Let's print out the content of that memory. So printf, or maybe let's change it. Let's change it and then print it out. So star px is equal to 1. And I would like to modify my print statement to both print the value of x and the address of it. So I'm just going to retype it. Printf x equals %d %x \n, end quote, x, comma, ampersand x. Save it. I'm going to recompile it. I'm going to try to run it. ./hi.exe. I can't say that I'm seeing any difference in my output. Did I not save it? I said I did. GCC just out to hi. ./hi. All right, okay. That I did something wrong, but when I compiled it again and ran it, I got my expected output. So what was my expected output? When it ran, it said that x was equal to 1. And then it printed out our memory address of the address of x. Well, how did that work? We declared x to be 0 and we never changed x. No, but we changed the value of the memory that was at the address of x. So this is what's known as a pointer. It's a pointer to x. And I precede all of my pointer variables with the letter P, just to indicate that it's a pointer. And so I declared a pointer x variable, and I signed into that variable the address of the x variable. And then when I wanted to store something into it, I did something called dereferencing. Dereferencing means use what's in that address. Don't use the variable itself. If I use the variable itself, I'm just, writing something out to px as though it's a regular variable, which it is not. It instead is a pointer. And so by doing star px, I'm able to change the memory at address FFFFCBF4 to put my new value in it. And we're going to be hitting this concept a lot. We're going to be talking about pointers a lot more. So this is just a first brush at the idea. Did everybody get that to work? Working for you, or are you taking the notes? Okay, cool deal. So that's the idea of pointers. I'm going to go ahead and add a comment. And this is change the contents of that memory address to a new value. When we print it, x is now equal to 1. So we have a whole bunch of types. Now they're not caps. When I stole this slide, I should have noted that the caps was wrong. They're lowercase. But a character is a single byte. It holds an ASCII value. What is an ASCII value? It's a way of encoding text. If you go to something like ASCIItable.com, then you'll see a list of ASCII values. So when we type in the word Bob, what it is storing out there is one of the bytes has got a 66 in it, another byte has a 79 in it, and the third byte also has 66 in it. And a byte can hold a value anywhere between 0 and 255. An int is an integer. It's 2 bytes wide. According to this thing, I think this is totally wrong, and I just need to delete this slide. I am so sorry. In our language, well, let's find out what size an int is. Let's find out what the size of an int is in GCC. We already played this game in Microsoft Studio. I'm getting tired of that hello message. I think I'm just going to change it to done. But above that, I'm going to printf size of int equals %d \n, end quote, comma, size of parentheses x, 2 closing parentheses and then a semicolon. I did restart the recorder, did I not? Good. All right, so save it, compile it, run it. And an int in GCC is 4 bytes. I'm sorry, I need to remake this this PowerPoint slide because the sizes are wrong. A short is 2 bytes long. Let's find out if a long is 4 bytes. Remember I was complaining about longs versus longs? Let's give this a shot and declare a long. So long, I'm just going to call it capital L, is equal to 3. And then the size of long is equal to size of parentheses L. Save it. Compile it. Run it. And a long is 8 bytes, unlike Microsoft C. See, this is how it ought to should. Microsoft is not the standard. However, like we said, you could always use the types specifications, right? Underscore, underscore. I'm not sure that those work for GCC. I've kind of spaced out on that. We looked them up last time. Does GCC have underscore, underscore, int 32, things like that. What, not 42. Is there a counterpoint? I don't think so, no. The recent few versions I've checked, you'll have that. Alrighty. Anyways, okay. We'll just trust that a long is at least the same size, if not bigger, than an int. And then you have the unsigned versions. The unsigned versions use the signed bit to store extra data so they can go twice as large, but they can cannot go negative. So for example, an int, here it says can go negative 32 to positive 32,000. Since it's actually a 4-bit number, it can go up to minus 2 billion up to plus 2 billion. And then the unsigned int version of it could go from 0 to 4 billion. So constants and variables. A constant is a literal, which remains unchanged during the execution of the program. A constant is a fixed value. It cannot be altered during the execution of a program. C constants can be declared into two categories, primary constants and secondary constants. Now this concept, to me, is not nearly as important as, and I should have modified it, named and unnamed constants. I think I'm going to even add a slide there to that effect. Two, I'd already used the words, categories, two types of constants, named constants and unnamed constants, also called literals. So a primary constant are the main data types, integer, float, character, and string. Then there are secondary constants. You can define a constant that's an array, or that's a pointer, that's a structure, that's a union, and that's an enum. So an integer constant, a literal, must have at least one digit. I'm going to call this literal constants in my PowerPoint. So it should not contain a decimal point. It should not contain an exponent. When I said equals 0, that was an integer constant, an integer literal. If it's positive, you can put in a plus sign. You can leave it out. If it's negative, you better use the minus sign. You can't put commas. You can't put blanks. You can't put non-digit characters in your integer constant. So you can't do 1, 000 to mean 1,000. That's pretty much true of all the programming languages I've ever used. And the value of the constant cannot exceed the specified limit, which for an int, a signed int, is a little bit more than 2 billion. It cannot go larger than that. It cannot go less than negative 2 billion, about a little bit, and without doing overflow. Overflow is when the value is corrupted because it cannot fit in the number of bytes that's specified for it. So then we have real floating point constants, slash literals. So real values are often called floating point constants. There are two ways to represent a real constant, decimal form and exponential form. When you define a real constant, a floating point constant, you just throw in a dot. You know, if you say x is equal to 3, that 3 is an integer literal. But if you say x is equal to 3.0, it's a floating point literal. So in an exponential form of representation, the real constant is represented in two parts. Before the e, it's called the mantissa, and the part following the e is called the exponent. So if we wanted to, what's the speed of light? In meters per second. All right, it's that many k per second. 2, I'm going to write this type this in and then change it. Okay. So speed of light is that. I'm going to modify it so that it's exponential, 2.99 kilometers. So that's 1, 2, 3, 4, 5, e to the 5. But I want it to be in meters, so it's going to be e to the 8. Okay. Meters per second. Okay, so I'm going to just define a constant. Const, can I type? Const double c, like e is equal to mc squared, is equal to 2.99792 e to the 8. This is the exponent, and this is the mantissa. What is an exponent? It's just 10 to the power of. So it's 10 to the power of 8. I do not believe that it would compile if we put a fractional exponent in there. If I say 8.1, I would not expect it to compile. I'm going to prove that to myself. Because e is not a function for calculating powers, it's just a syntax. All right. It did not like that. Not surprised. I'm going to go and remove the invalid bit, that .1 there, because that was dumb. Can I put a space there? Can I pad out the exponent format? Nope. Okay. I guess I should have tried it correctly before I started messing it up. And that worked. Okay, so I've declared a constant called c. Is c a great variable name? Not really. If you're familiar with it and you're saying that you're calculating e is equal to mc squared, great. We could have called it speed underscore of underscore light, and I would have been happier.
So did you say earlier doubles are like floats except they're not negative?
No, there's no unsigned versus signed floats. All floats are signed.
Okay.
But you can have unsigned ints, unsigned longs, unsigned bytes, unsigned shorts, unsigned chars. And those are the ones that can't be negative, but they hold twice as large a value because they get to use their sign bit, that first bit in the byte, in order to do it.
So what are the doubles again? I feel like
A double is just a double wide floating point. A floating point number, a float, takes up 4 bytes.
So it's just a 2 times bigger.
Right.
You can store it.
Which gives much more precision. A float has like about 8 digits of precision. So you could type in point 1, 2, 3, 4, 5, 6, 7, 8. A float, excuse me, a double has about twice as many points of precision, 16 points of precision. But even more importantly, perhaps, if you're trying to keep track of large numbers, the maximum exponent of a float is like 34, something like that. And the maximum exponent of a double is like 300, something like that. So it can do much more precise numbers and much larger numbers. And so in general, I just use doubles because I feel like being more precise. I bet the slide back here, if I trusted it, if it said that a double was an 8-bit number, which it does, all it says is approximately 15 bits of precision, but it doesn't get the maximum exponent. Let's see if we can look it up.
So doubles can be negative too?
Sure.
That's weird.
Well, like in a negative number, you know.
Yeah,
what's
I understand, but it's
yeah.
weird that like the other ones can't be, but they have.
Think of it, maybe this will help, but the unsigned variants are the oddballs. I would say that everything should be able to hold positive and negative. It's just that they're kind of hacking the format of it to use the sign bit as an extra piece of data so that the unsigned ones can go twice as large. And why isn't there an unsigned double? So that you can, eke out a little bit more data on them? I don't know.
How would you do it if you wanted like even bigger number?
You would have to use a specialized data type, and I'm not sure of the data types.
Because I know like people that do math, they count like prime numbers and they go on forever.
Right. They you millions upon millions of digits and stuff like that. There are libraries that hold values larger than doubles. This ints and floats and doubles business follows ANSI standards or IEEE standards for how data is stored in 4 bytes or 8 bytes. And then things like that are not part of the hardware standards. So they're up to the language and the language's libraries to figure out how they were going to handle numbers larger than that. For example, the Python programming language, an int, is not limited to plus or minus 2 billion. You can have really, really large integers. So, very good questions, especially when I don't know how you would do. There is a type called long double, but I believe it's also just 8 bytes. If I go back to my editor and I change this double up here that I had, and made this a long double, and then ran it, what's it going to say the size is? Okay, there is a larger version of double. There's long double, which could hold a vastly larger number. I have no idea of the limits. I'd never looked up long doubles before. You gonna tell me? I'm not gonna look it up. If you were curious, you could look it up. Alrighty, and that's in C++ anyways, which might be a slightly different standard. Hopefully they would be the same, since the same compiler would be working on both of them. So a character is just an integer type. It's just an integer type that's a single byte. Have I done the bits lecture? Have I gotten on the board and drawn bits and a car odometer and binary and stuff like that?
I don't think so.
Don't think so. Okay.
I mean, there's like
Are we real comfortable with the idea of bits because we've had them in previous classes? Yes or no?
You know, like 8 bits in a byte.
Right. Okay, so what we're going to do, and sorry for the guys who aren't here and are watching the video, you're not going to get to see what I'm writing, but you'll get to hear it. Maybe I can do it on Notepad for a while. Is a bit is a 0 or a 1. The signal is on. The current, there's current or there's an absence of current. A byte is 8 bits. Why do we have bits? What's special about figuring out the way bits work? If we had a car and we were driving along in base 10, we have 10 digits, 0 through 9. If we were going to start counting and we were a computer, we wouldn't start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We would go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now that's still 10 different values. It's just that 0-based indexing means that we counted 0 as part of it. So if you're driving your car, the odometer is increasing. Now we have maxed out. We have gotten to the largest digit that can hold. And I know everybody knows this intuitively. But what happens here? When we go one more mile, we need to increment that place. But it's maxed out. So we have to reset it back to 0, and then we increment the next place. And so this is the 1's place, that's the 10's place, and that's the 100's place. Or we could word it as the 10 to the power of 2 place. Remember, there is no exponent operator. 10 to the power of 1, and then 10 to the power of 0. 10 to the power of 0, every number to the power of 0 is 1. We could write a mathematical proof, but just accept it. Okay, so when I incremented 9, that had to reset to 0 because it was maxed out, and we incremented the next column. And say I kept driving, right? I don't need to keep repeating that over and over and over, but I got to 99. And I needed to increment that column yet again. Well, it's maxed out. We would reset it back to the lowest digit, and we would increment the next column. Well, that one's maxed out too, so we would reset that place and increment the next value. That was supposed to be a 0. And then a 0 cranks up to a 1. And we could keep driving until we got to 999, and then the car would explode. No, I'm kidding. But what happens is we're going to add 1 to that, and we know what happens there. If our odometer only showed 3 places, they would all be reset back to 0. That's called overflow. That's when you've maxed out the amount of data that can be stored in 3 decimal digits. So for binary, we're not going to do 10 to the powers of, we're going to do 2 to the powers of. 2 to the power of 2. 2 to the power of 1. 2 to the power of 0. So we hop in our binary car. We drive a mile. Now we're going to drive another mile. No, we can't do that because binary only has 2 digits. 0 and 1. So after we've gotten here, this column's already maxed out. So if we're going to go another mile, if we're going to increment that column, we have to reset it back to the lowest value and we increment the next column over. All right. Now 0 is no longer maxed out, so I can increment it again. Now 0 is maxed out again, so I got to reset it back to 0. I'm going to increment that column. Whoops, that's the largest digit that the system supports, so I set that back to a 0, and I do that. Now I'm going to drive a little bit further. I'm not going to keep saying that maxed out business. I'm hoping you see the way that I'm counting it. Past that, kablooey. We've exceeded our ability to hold data. So 3 bits. How many different values were we able to do? I'm going to count them off. That's a 0. That's a 1. That's a 2. That's a 3. That's a 4. I'll give reasons why in just a minute. All right. So if the largest value is 7, we have 8 different possible values. So 3 bits can hold 8 different values. Now, if this was assigned, meaning that you could have positive and negative values, well, how could you store negative values in here? What happens is that a signed type uses the first bit to indicate whether it's positive or negative. That lowers the maximum value that you could store in it, right? Because now all of these numbers are negative. So the largest value you could store in a signed 3-bit value would just be 3. But then you could also store some negative numbers in it. And it's not as easy as saying that, okay, if you set that, then it means it's a negative number, because what would negative 0 be? So it does something called 2's complement, which I'm not going to figure out what the 2's complement of those numbers are. So just broadly speaking, I'm going to say 3 bits can hold 8 values. How about 4 bits? 4 bits, if you count from 000 to 111, is 16 different values. There's a formula. 2 to the power of n is the number of different values. So 2 to the power of 3 is 8. 2 to the power of 4, 16. All right. How about bytes? 2 to the power of 8, because there's 8 bits in a byte. It didn't have to be that way. When they were inventing computers in the 60s, some people picked a word length of 10 bits, some people chose 14 or whatever. It just turned out that 8 was a nice, handy value. Powers of 2 are nice and fast for chips to handle. And so they picked the smallest unit of information that the Intel processor can handle as 8 bits, being a byte. So that's the smallest amount, and that is used for memory addressing. You say, I want byte number 75, I want byte number 76, byte number 77, and it's going to go and pull 8 bits back out. So anyways, 2 to the power of 8 is 256. So if we had 8 bits, we could go from 0000, 0000 out to 1111, 1111, like that. And so that's 256 different possible values. If I wanted to add this up and to prove that all those ones equal 255, I could do so. We would just figure out the place values. This is 2 to the power of 0. Every number to the power of 0 is 1. That's 2 to the 1, 2 to the 2, come on, 2 to the 3, you see how this is going, right? 2 to the 4, 2 to the 5, 2 to the 6th, and 2 to the 7th. Those are the place values we have. So if we had this number, 1, 0, 1, 0, 1, 1, 1, 0, we could add them up. This is a 128 plus, do we have any 64s? No. So 128 plus a 32 plus 8, do we have any 16s? No, so I'm going to skip that. Plus an 8 plus a 4 plus a 2. Do we have any 1s? No, we do not, so that's it. And if we added all those numbers up together, pretend we can, I'm just going to copy and paste them and find out the answer.
Just 190.
Okay.
And you can just do that number you had minus 65, right?
So 174 supposedly. Whoops. And if I did them all, 128 plus 32, no wait, 128, if I did them all, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, that's 255. So if you had to calculate, if you had to convert binary to base 10 by hand, that's how you would do it. Going the other way is a different process. It's a weird process where you divide everything by 2 and you keep track of the remainder. So 174. I want to figure out what the binary representation of 174 is. What I would do is I would divide everything by 2. 174 divided by 2 is 87 with a remainder of 0 because it was an even number, right? 174 divided by 2 cleanly divides. Now 87 divided by 2 is 43 with a remainder of 1. 43 divided by 2 is 21 with a remainder of 1. 21 divided by 2 is 10 with a remainder of 1. 10 divided by 2 is 5 with a remainder of 0. 5 divided by 2 is 2 with a remainder of 1. 2 divided by 2 is 1 with a remainder of 0. And 1 divided by 2 is 0 with a remainder of 1. And then you take your numbers and you write them from the bottom up. 1, 0, 1, 0, 1, 1, 1, 0. And hopefully that's the same thing I had up here. 1, 0, 1, 0, 1, 1, 1, 0. So then write them from the bottom up. All right, so if you have a 30 ints in GCC and in Microsoft land, I don't remember what they call their compiler, are 4 bytes long. 4 times 8 is 32 bits, so 2 to the power of 32 is about 4 billion. 2 to the power of 32, about 4 billion. But again, if we're going to use the sign bit in order to allow negative numbers, you know, I didn't do this with the 8-bit byte. But if we had 0, 0, 0, 0, 0, 0, 0, 1, out to 0, 1, 1, 1, 1, 1, all those different choices, that would be 127. And then if you counted all the negative numbers, that's equal to negative 1 and 1 0 0 0 is negative 128 for reasons I'm not going to go into because I don't ever remember how to do 2's complement. But anyways, so by using the first bit as our sign bit, we're only allowed to get half as high. Remember, we said that 8 bits unsigned gives us max, or 200, gives us values from 0 to 255. 8-bit signed gives us values from negative 128 to positive 127. This is a range of 256. This is also a range of 256. It's just chopped into half so that we can accommodate negative numbers. So unsigned 2 to the power of 32 gives us the range from 0 to about 4 billion. and signed to the power of 32 range from about negative 2 billion to positive 2 billion. Okay, while we're on the topic, I'm going to talk about and or. And means both cases have to be true for the result to be true. Like if you're going to go out to eat. If you're going to go out to eat, two things that better be true. One, you better have money, and two, you better be hungry. If you're not hungry, you're not going to go eat. If you don't have any money, you better stay home. So, something like this. If hungry and we have money, then go out to eat. Right, so they both have to be on. Both operands have to be on for the result to be true. Or works a little bit differently. One or the other, or both, have to be true for the result to be true. So like if you're going to stay home, can I stay home? If sick or tired, then stay home. Right? I'm going to stay home if I'm sick. I'm going to stay home if I'm tired. And then I'll get fired if I do that too often. But anyways, so or means that only one side or the other or both have to be true for the result to be true. We can create a truth table for and or. So here's the and truth table. I'm going to do capital F's for true and false. F and F. F and true. True and F. True and true. Only one of these cases is true, and which is that? Remember that and both operands have to be true for the result to be true. So which of these is going to be the ones that evaluates to true?
True and true.
Yep, true or true is equal to true. The rest of them are false. All right, now we're going to do an or truth table. Same thing. F and F, F and, no, excuse me, or F or T, T or F, T or T. Only one side has to be true for the result to be true. So this is false because neither one is true, but the rest of them are all true. Now, if you're an electrical engineer, there's one called exclusive or. Exclusive or means one side and only one side is true for the result to be true. If they're both false, the answer is false. If they're both true, the answer is false. I'm going to kind of skip that for now. And then there's one more called not. Not false is equal to true. Not true is equal to false. Right? If you're hungry, if hungry is equal to true, then, but if you're not hungry, then is that true or false? No, because you were hungry, so that's false. Okay, we're going to replace F and T with zeros and ones. So I'm going to say X and Y and result. Zeros being false, ones being true. So this is the and truth table. Expressed in binary. So 0 and 0 is 0, just like false and false is equal to false. In fact, there's only one condition that's true when you're talking about and. Notice there's only one condition that's true when you're talking about and. There's only one condition that's false if you're talking about or. All right, so we're going to keep rocking this. 0 and 1 is still false. 1 and 0 is still false. 1 and 1 is true. Now we're going to do the or truth table, and I'm just going to copy and paste this and change the words in the results. So If we're doing an OR truth table, if either one of them is set to 1, then the result is 1. So neither one of them are set to 1 here, so the result is still 0. But here one of the sides is set to 1. Here the other side is set to 1. Here both sides of them are set to 1. And okay, we're going to get wonky and put the XOR truth table in there. You don't have a keyword for XOR, but you do have a symbol for performing the XOR operation. Okay, and so in this case, if both of them or neither of them are true, then the result is false. Otherwise, the result is true. One and only one side, exclusive OR. So that's false. That's true. That's true. And this is back to false. And there's all sorts of other variants if you're an electrical engineer. There's NAND. NAND is just a flipped version of AND. I'm not going to even create it. I guess I am. It's easy enough, right? So this means get the result, but then flip it. And NANDs are pretty dang important in electrical engineering. When you talk about flash RAM, it's all composed of NAND circuits, you know, incredibly small.
So that'd be 1, 0, 0, 0.
Did I not flip them all?
No, because it's and, right? It's flipping and, not or.
No, this is still correct because it's the same thing as saying not and, which means you flip every result. And so that 1 becomes a 0.
Okay.
Yeah.
I misunderstood what you meant by flip.
Yeah, sorry about
You
that.
meant, like, flip the actual order.
Right, and so there's also NOR, not flipping the order, but flipping the result. So you could take your OR truth table and do a NOR truth table just by flipping the resulting bit. Yeah, I see exactly why you said that. Okay, so that would be that, that would be that, that would be that, that would be that. I don't think in those terms, really. I just think of ands and ors and nots. And that's the way our if statements and while statements, you know, are written. This is more wonky. And there are operators for doing XOR as well as doing and not and or. I guess if you wanted to do a NAND, you would just AND the two values together and then use not to flip them. Okay, so in our language, unlike Python, if we want to do AND, the symbol is ampersand, ampersand, shift 7, shift 7. If we want to do OR, it's 2 vertical bars, shift backslash. If we want to do bitwise, we want to just take 2 numbers and flip and modify their bits rather than doing Boolean true and false. It's a single ampersand. So a bitwise AND is a single ampersand. A bitwise OR is a single bar. Now what do I mean by that? Say if we had this number. I'm just going to make up a 4-bit number. 0010. And then I'm going to have another number like that. And I want to AND those 2 guys together bitwise like that. So what is that and that? Just out of curiosity, let's convert these to decimal. Are there any 8s? No. Are there any 4s? No. But there is a 2. And there's no 1s. So this is the equivalent of 2 bitwise ANDed with, now there's an 8, but no 4s, and there's a 2, so that's a 10. So we're going to figure out what AND of 2 and 10 are. We're going to just stack them on top of each other, and then we're going to follow the rules of our AND truth table. But instead I'm just going to do it on the fly. For AND to be correct, for the result to be true, both bits have to be true. So in that column, are both bits true? No. In that column, are both bits true? Nope. How about this one? Yes. Both bits are true there. And here, both bits are true. And so if we added that one back up, this is again equal to a 2. So counterintuitively, perhaps, 2 and 10 is equal to 2. Odd but true. Let's do one more. 0, 1, 1, 0, 1100. Trying to come up to something that won't give us the same answer as one of the operands of the operation. Okay, so this one is there's no 1s, but there's a 2 and a 4, so that's a 6. What is this one equal to? Just add that up in your head and tell me. That's a 12, correct. All right, so we're going to do 6 and 12. We've stacked them up. So bitwise, what does that equal to? Just tell me all 4 bits. 0, 1, 0, 0. Which is, in decimal, what does that equal to?
4.
4, right, okay. So, turns out that 6 and 12 equals 4. Now, why in the world would you want to know that? Well, when you're manipulating bits, sometimes you want to isolate a certain number of bits. If you're talking like about internet packets, the internet packet, the headers, are defined according to a protocol, TCP header. This may not give a good example of it. Well, here we go, like this. You know, the first 2 bytes is the port number, the next 2 bytes are the port number. We get to a point here where the data offset is 4 bits. Say we wanted to get those 4 bits and manipulate them. We could read in this byte here, 4 bits and 4 bits and that one more. We could read in the byte and then we could mask off the first 4 bits to find out what those bits were, ignoring the rest. So let's get the first 4 bits of a number using AND. And what we would do is we would AND it against 1, 2, 3, 4, 5, 6, 7, 8. So no matter what the number was, like that, if we're going to figure out what it is, what's our result? This is a 1 and a 0 is 0, 1, 0, 1. And then are the rest of them zeros? And the answer is yes. So we have figured out that the first 4 bits is that. What if we wanted to turn those into a number like between 1 and 15 or something? Because right now they're not between 1 and 15, right? They're much larger numbers. You could do a shift right 4 bits. What does shift mean? Push them over, right? So if you have the number 11000000 and then you shift it 1, then it becomes 0110000. You shift it again, I always mess this up. Now is about the point where we're going to start losing data. We would have been losing data all along if some of these others were 1s, right? And then lastly, one last bit, and boom, we've lost all of our data. So that was shifting 1 bits. This was shifting 2 bits, 3 bits, 4 bits, and so on. You can shift to the left and you can shift to the right. Shifting to the left by 1 bit. What? I guess that's correct. If you shift any number more than the number of bits, then it's going to be completely wiped out, regardless of whether it's right or left. I'm just going to pick a number and then I'm going to shift it 1 to the left and show you something. Except I'm going to do 4-bit numbers just because they're easy, right? Okay. And then I want to shift that 1 bit to the left. And that's not the symbol, and I need to remember what the symbol really is. But what does that become? We shift it 1 to the left, and what's the new 4-bit representation? 0011. Now let's figure out what those are. What is 0110? That's a 4 plus a 2, so that's a 6. What is 0011? 3. Okay, so by shifting to the right, I think I've been saying left. By shifting to the right, that's the same thing as dividing by 2. An extraordinarily fast way of dividing by 2. It doesn't even involve any math at all. It's just shifting. So dividing and multiplying by 2 is exceptionally fast. So if we took this and we shifted it that way, we went the other way 1 bit, we would get 1100. So that's still a 6. And I gave it away by saying that it was 12, but we could add them up. That's an 8 and a 4, and that's a 12. So shifting right 1 bit is the same as multiply by 2. No, divide by 2. Shifting left 1 bit is the same as multiplying by 2. Now, why am I taking the time to talk about all this stuff? Because if you're doing C programming, it's probably because you care enough about these kind of numbers to be wanting to manipulate the bits. One more thing I wanted to mention, but we're just about out of time, which is that that OR truth table looked kind of like this. 0 OR 0 equals 0. 0 OR 1 equals 1. 1 OR 0 equals 1. 1 OR 1 equals 1. But if you're doing and 0 equals 0. 0 and 1 equals 0. 1 and 0 equals 0. And then 1 and 1 equals 1. So think about if you replaced OR with a mathematical symbol for addition. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1. Well, if you had a logical universe where you only had 2 possible states, 0 and 1, then 1 plus 1 is in fact 1. Not bits, just possible states, true or false. That's Boolean. Boolean math consists of only trues and falses. Now, what if we replaced and with multiplication? 0 times 0 is 0. 0 times any number is 0. So 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. So and is the equivalent, the Boolean equivalent of multiplication. Whereas OR is the Boolean equivalent of addition. No, yeah. Do I got that right? Yes, I do. So when you're writing logical phrases like if x and y, you could write if x, y. If you ever take a logic class, you might do that because and is multiplication. If you need to write if x or y, you would do if x plus y, that kind of thing. And you might put a space between them in order to indicate it, but okay. You could put the multiply if you really wanted in there. Alrighty, let's make a Dropbox for our file. I didn't get far enough in my Bitwise lecture to give y'all homework about that. Alright, I'm just going to create a homework assignment really quickly. Write a program using scanf to ask the user for their height in inches and their weight in pounds. Then calculate their BMI, stands for body mass index. The formula is BMI equals weight divided by height times height in inches. Then print out the height. And that's not really enough homework. Check again tomorrow and I may have others uploaded of all of the equivalent difficulty.
Do you mean print out BMI?
Yeah, I apologize for that. Print out the BMI. And let's make it slightly more difficult in the format of this. If you weigh 200 pounds and are 62 inches tall, your BMI is, I'm going to change this to 180. I kind of know these numbers. BMI is 26. That's not a correct answer. These aren't. Not a correct calculation. Guess we could figure it out. 80 divided by 70 squared. Times 703. I may not have put that in a formula, but it's true. Aren't you going to... Well, that's not right. Okay, forget it. 80, 180. $25.8. Whatever. Why don't I get the actual value? If I'm being lazy, I may as well do this. I'll be curious to see how precise your calculation gets, how closely it matches that. I messed up the formula. It's weight times 703.0 divided by height times height. I would use doubles the whole way through. You might try both just to see how it works out. If we had done looping yet, I would ask you to write the program to loop until you were tired of entering this data. That's enough. That's enough. All right, gang. Coming up to the point where I need to be ready for the next class, so I'll save that, upload it as homework 2, and let's make a Dropbox. And everything that you've turned in so far will be graded by tomorrow, all the grades exported. And so we need an E. All right, so you should see 2 Dropboxes, today's and the homeworks, and I will upload today's notes and create a homework document.
It's just the .c file that we're uploading, right?
Right, go ahead and just upload the .c file, the hi.c. All right. Any questions? Are we all good? All righty.